Welcome to the Explainer. I am absolutely thrilled you're joining me today. If you've been following the rapid evolution of AI, you already know we are hitting an incredible frontier. But right now, behind the scenes, there's a fascinating and honestly almost invisible hurdle researchers are actively battling. Today, we're going to look closely at how AI actually learns to navigate highly complex, multi-step problems in the real world. We'll be unpacking a groundbreaking new framework called AEM, and by the end of this explainer, you'll understand exactly how AI is learning to master the art of self-correction.
So, to really grasp the magnitude of this breakthrough, we've got to start with a fundamental question. In the field, it's known as the credit assignment problem. Think about a soccer team, right? They pass the ball back and forth 50 times before finally scoring this magnificent goal. When the team celebrates, how do they know which specific pass was the genius move that actually cracked the defense? Or imagine dropping an AI into a massive, sprawling maze. If it eventually finds the exit, how does it figure out which of its hundreds of left and right turns were the actual right ones, and which were just lucky guesses? Section 1. The Sparse Reward Problem.
And that brings us to the first massive roadblock in training autonomous agentic AI today. You see, large language models, or LLMs, well, they aren't just passive chatbots answering our trivia questions anymore. They're evolving into active agents. We're deploying them to browse the web, navigate user interfaces, and even write complex software code autonomously in environments like SWBench Verified. They are out there executing long, interactive trajectories where they literally have to make sequence after sequence of decisions.
But here's where it gets incredibly frustrating for the AI during its reinforcement learning training. It suffers from what we call sparse rewards. Basically, the AI only gets a simple pass or fail, a single thumbs up or thumbs down at the very end of a task. It might take 50 complex steps to try and fix a GitHub issue, but it only receives one final grade. And because it gets zero feedback along the way, all 50 intermediate steps get the exact same indistinguishable learning signal. If it actually succeeds, it has absolutely no idea which of those 50 steps was the critical, brilliant move, and which ones were, well, practically useless. Section 2. The Credit Assignment Mystery. So, how do we actually solve this? Well, let's look at how the industry is trying to crack this mystery right now, and why those methods are falling short. Honestly, up until now, the solutions have been incredibly bulky. The first approach uses what are called process reward models. Think of them like expensive private investigators hired to sit there, watch, and grade every single intermediate step. But doing that requires building entirely new models and relies heavily on super expensive human annotation. The second approach is tree-structured optimization that maps out branching trajectories, but it incurs massive computational overhead that just does not scale well when you have multi-turn settings. And finally, self-supervised methods try to guess the signals, but they suffer from heavy bias and really restrictive structural assumptions. Long story short, it's just way too costly and too slow. Okay, let's dive into this directly from the source paper. The authors write, and I quote, "These limitations call for a scalable, fine-grained credit assignment framework that does not rely on extra supervision, heavy computation, and restrictive structural assumptions. Basically, we need an elegant savior here, something mathematically sound that isn't going to totally blot the training process." Section 3. Entropy, the hidden signal. And that need leads us straight to the unlikely hero of our explainer today. It's a concept hidden right inside the AI itself, entropy. Now, if we strip away all the dense mathematical jargon for a second, what actually is entropy in this context? Simply put, entropy is the AI's intrinsic level of uncertainty. It's literally a built-in behavioral measure of the model's curiosity. It's a signal that exists entirely within the policy itself, which means it requires zero outside judges or extra reward models to calculate. Think of it like a compass with two poles. On one end, you have high entropy. This is exploration mode. The AI is highly uncertain, which means it's actively trying crazy new things, seeing what works, and mapping out that maze we talked about earlier. On the other end, you have low entropy. That's exploitation mode. The AI has figured out a path that actually works, its uncertainty naturally drops, and it confidently doubles down on executing that specific winning strategy. Now, what the researchers mathematically proved, and you can notice the geometric representation of this here using Fisher-Rao metrics, is that entropy drift is governed entirely by a response's advantage and its relative surprisal. We definitely don't need to get bogged down in the complex equations today, but what you absolutely should take away from this is that the AI's own internal uncertainty can literally serve as a built-in compass for learning. The mathematical structure to do this, it's already there. Section 4. Introducing AEM. So, armed with that mathematical proof, the researchers built their solution. Let me introduce you to AEM, which stands for Adaptive Entropy Modulation. And honestly, AEM is brilliant in its simplicity. It's a highly lightweight, plug-in method that requires zero extra supervision. Instead of adding a bunch of new models, AEM just takes the AI's existing internal entropy signal, that uncertainty proxy, and uses it to automatically rescale the advantage of each response. Essentially, it automatically shifts the AI's gears. Early in training, it forces the AI to keep its entropy high, which preserves curious exploration. Then, as the AI starts succeeding more often, AEM smoothly promotes exploitation, locking in on those successful behaviors.
Section 5. From exploration to exploitation. Let's see how this actually builds visually, using data straight from the source experiments. This brilliantly illustrates the exploration phase. Look at the entropy trajectories over 150 training steps here. The blue lines are the baseline models, and notice how their entropy just plummets almost immediately? They essentially get stuck in a rut, confidently doing the wrong thing. But the orange lines, those are the models equipped with AEM. AEM prevents that premature entropy collapse. It forces the AI to maintain a higher entropy early on, demanding that it keeps exploring and trying new things until it genuinely finds the right path. And then just look at this dynamic transition. Notice the really clear cause and effect narrative happening here. The solid line is the success rate climbing up. The dashed line is the entropy. See what happens once the AI actually starts finding the correct solutions and the success rate skyrockets? AIM immediately adopts. It intentionally lowers the entropy to exploit that newly discovered winning strategy. It seamlessly transitions from curious explorer right into confident executor.
Section 6. Results without extra cost.
All right, let's look at the empirical proof. Why does this elegant, math-driven approach actually matter for the real-world applications that we care about? Well, AM produces massive leaps in success rates across some incredibly diverse agentic tasks. We are looking at an 8.8% gain in complex household reasoning tasks in AlfWorld and a 5.6% gain in autonomous web navigation in WebShop. But I really want to highlight that bottom row for you, SWE Bench Verified. A 1.4% gain there is highly significant because that benchmark requires the AI to autonomously resolve real-world GitHub issues. That means the AI is getting measurably better at writing real, functional software code entirely on its own. So the crucial point here is this. Even when researchers applied AEM to state-of-the-art frameworks like DeepSway, which runs on massive 32 billion parameter models, AAM still consistently drove performance higher. You can see the orange line of DeepSway plus AAM definitively pushing past the already powerful baseline. It just proves that entropy-aware credit assignment is universally complementary. Now, with performance boosts this impressive, especially compared to those bulky process reward models we discussed earlier, you're probably wondering about the catch, the computational cost, right? How much extra time does this actually take to run?
Well, what's really interesting is exactly that cost breakdown. Look at that tiny orange sliver right there. AEM accounts for just 1.1% of the per-step computation time. Because AEM uses the data already generated during the AI's regular forward passes, it requires zero extra neural network rollouts. The computational overhead is virtually invisible. You are getting smarter, far more capable agents for practically free.
Which brings us to our final thought for this explainer. We've seen how unlocking the credit assignment mystery using the AI's own intrinsic entropy fundamentally changes how these models learn. If AI agents can now automatically and efficiently balance their own curiosity with confident execution without us having to hold their hand every step of the way, what highly complex, multi-step human tasks are they going to master next? I'll tell you one thing for sure, the ceiling for autonomous agents just got a whole lot higher. Thank you so much for diving into this fascinating topic with me today, and keep exploring.